Step-by-step exam solutions. Okay, physics class, training you to excel. Subscribe to step-by-step exam solution. Like this video. Share the link of this video with others. Click for alert so that you receive the next video when released. Please drop your comments to serve you better. Okay, physics class, present 5 steps to exam success. Step 1, pray. Step 2, plan. Step 3, preview. Prepare. Step 4, preview. Step 5, you perform. These are 5 steps to exam success. Okay, physics class, step-by-step exam solution to nuclear energy calculations. In this presentation, we will be studying the following. Number 1, the binding energy of the nucleus. Number 2, the mass defect. Number 3, the Einstein's mass-energy relationship. The objective of these presentations are: number 1, explain the binding energy and the mass defect of the nucleus. Number 2, use Einstein's mass-energy relationship to calculate the energy released during nuclear fission reaction. Number 3, state the units of atomic energy and convert from one to another. And other things we're also going to study as we continue in the discussion. Now we go to the next slide for the presentation proper, nuclear energy calculation. Before then, we need to actually understand what nuclear energy is. Nuclear energy or nuclear reaction deals with the changes that happens inside the nucleus of an atom. Whenever there is a rearrangement of the particles of the nucleus of an atom, a new element is always produced, and that changes in the structure is what leads to the release of nuclear energy. The process this can be achieved can be: number 1, splitting the nucleus or separating the particles of the nucleus, the protons and the neutrons. Number 2, bringing them together, fusing them together, joining them together. These are 2 ways this can be achieved. In whichever way energy is released, that's very important. In whichever way energy is released. Now we are looking at the binding energy of the nucleus. What actually is the binding energy of the nucleus? The binding energy is the glue, the super glue of the nucleus. It is the energy that keeps the nucleus stable. The higher the binding energy per nucleon, the more stable the nucleus is. Then definition. Binding energy of a nucleus is the minimum energy required or needed to separate it or to separate its particles into its basic particles. And these basic particles are the protons and the neutrons. That energy supply to separate the protons and the neutrons is what we refer to as the binding energy. The binding energy of a nucleus can also be defined the other way. Remember, it has to do with either splitting or fusing. Now let's look at the situation where they join together. It can also be defined as the minimum energy required for the nucleus to join together to form the basic particles, including protons and neutrons. That energy required to bring the particles, the protons and neutrons together and fuse them together to become the nucleus is also what we refer to as binding energy. Now, the binding energy of a nucleus is related to the mass, to the change in mass that occurs during the fusion or the breakup of its particles. Yes, the binding energy, as I said, is equivalent to the loss or the gain in mass when these particles are joined together or separated. So now, having said so, then we're now going to look at the mass defect. What is the mass defect? Very simple. In its simplest term, mass defect is the difference between the calculated mass of the nucleus. If you add up all the particles, the protons and the neutrons, and the actual mass of the nucleus, that means the nucleus before you separate them, the mass before you separate them. If you find the difference between these two, that difference is what we refer to as the mass defect. In other words, here we have a particle, the nucleus. Now we separate the nucleus into its constituent particles. And now you have the mass of the protons and the neutrons all together giving us 20 grams. But before we separated them, the mass of the nucleus itself is giving us 19.26 grams. So now when you find a difference between the mass of the nucleus and the mass of the individual particles, then you are going to notice that the mass defect, delta M, is just 0.74 grams. So now this gain in mass or loss in mass, depending on whether they fuse together or they are separated, is what we refer to as mass defect. So therefore, when protons and neutrons come together to form a nucleus, the total mass of the nucleus is less than the sum of the individual masses of its basic particles, of its constituent particles, called the nucleus. This difference is known as mass defect. How do we define mass defect? Mass defect is the gain in mass produced when the constant particles of the nucleus, protons and neutrons, are separated. It can also be defined the other way around. It is the loss in mass when the basic particles of the nucleus, the protons and neutrons, are joined together. So now, if that's the two definitions stand, depending on whether we are splitting or fusing them during that chemical or nuclear reaction. Therefore, the mass defect, delta M, is given by the sum of the masses of the protons and the neutrons minus the mass of the nucleus itself, or the nucleon. So now, what does these symbols we are using here stand for? Delta M stands for mass defect. The MP stands for the mass of proton. The Mn stands for the mass of the neutron. Then the M standing alone stands for the mass of the nucleus. So these are what they represent. In calculation, you must specify, you must write down the meaning of these symbols we are using for you to gain the mark for the formula. So now we are going to look at the next, Einstein's mass energy relationship. This is the most important formula in physics. I refer to this as the most important formula in physics, and that is known as the Einstein's famous equation. E is equal to mc squared. This equation tells us that the mass and energy are equivalent. We can change mass to energy, and we can change energy to mass. So what does E stand for? The energy. And what does M stand for? The mass defect. And what does C stand for? The speed of light. Having explained this now, we are now going to look at atomic mass unit and the electron volt. Atomic mass unit is the mass of atomic particles. This mass is very, very tiny, small, that if we measure them in kilograms, they will be very, very small. So we need to measure them in another unit. The same thing has to do with atomic energy, or energy released during nuclear reaction. They are usually very small, that if you measure them in joule, they will be very, very small. If you measure them in joule, they will be very, very small. So we need to measure them in electron volt. So therefore, what are we saying here? The masses of atomic particles, protons and neutrons and electrons, are tiny. If we measure them in kilograms, they are very tiny. So therefore, we better measure them in another unit called atomic mass unit, mu. Most of the times we write that as U. Now, one atomic mass unit, or 1U, is equivalent to 1.66 times 10 raised to power minus 27 kilograms. That's one atomic mass unit. Now, a mole of any substance contains 6.02 times 10 raised to power 23 atoms. That's 1 mole of a substance. So in that case, if we have a mole of uranium-235, it's going to contain 235 grams And therefore 235 grams of uranium-235 will contain 6.02 times 10 raised to the power 23 atoms. That's very large number. So now, these are very important as we are going to be dealing with nuclear energy calculation, and you need to understand this. And please don't forget this. Write it down somewhere and keep it very close to you. So now we're now going to go into nuclear energy calculations. Nuclear energy calculations. We start by where we stop in the other slide. The mass defect of carbon 14 is given as this or this in kilogram. Therefore, 1 gram of uranium-235 contains 1 over 235 times 10 raised to the power 6 raised to the power 6.02 times 10 raised to the power 23 atoms. Now, atomic energies are also too small to be effectively measured in joules. Therefore, they are measured in a smaller unit called electron volt. I already mentioned that before. 1 electron volt is the equivalent to 1.6 times 10 raised to the power minus 19 joules. Then, what's the implication of all this? 1 atomic mass unit, 1 U, releases 931 mega electron volt, or if converted to joule, 1.4896 times 10 raised to the power 10 joules of energy. That's 1 electron, 1 atomic mass unit, the energy to release in joule. Now, if that is the case, we need to understand these things because in calculations, we are going to employ them in carrying out calculations. And now that's why we're starting with calculation number 1. And what is it? Calculate the mass defect and binding energy of alpha particle when the particles of the nucleus are fully separated. So now, all the information required in the calculations are given. The mass of the proton in kilogram, the mass of the neutron in kilogram, and then the mass of the alpha particle, nucleus or nucleon in kilogram, then the speed of light. Now, using all this information, we are going to calculate the mass defect of alpha particle and also the binding energy of alpha particle, that energy that keeps those particles together as a nucleus. Let us solve these questions now. So we are going to start by step number 1, add up the masses of the individual protons and neutrons. Then you will find the mass defect by subtracting the summation of the masses of the particles from subtracting it and the mass of the nucleus. And then we applied Einstein's mass energy relationship to calculate the binding energy. Now let's do that now. So we start. The mass defect, as we know, is given by the summation of the sum of the masses of the protons and the neutrons minus the mass of the alpha particle. You know what these symbols represent. Please do well to explain them. So number 2 steps, we make direct substitution into that formula. So when we do that, we simplify that. When you simplify that, we are going to have what we are having on the screen now, which will finally give us the answer as 0.051 times 10 raised to the power minus 27 kilogram. This is the loss in mass when these particles are brought together to form the nucleus, or the gain in mass when the alpha particle nucleus are fully separated. So now that you have the mass defect, we now apply this famous equation, Einstein mass energy relationship, E is equal to mc squared. Now please remember, E is energy, m is mass defect, c is the speed of light. You must explain that. Then we make substitution. The mass defect is this, 0.0151 times 10 raised to the power minus 20, you put it here. Then the speed of light is given as 3 times 10 raised to the power 8 meter per second. You multiply it by itself, or you can square it depending on your choice. Now using calculator, you can carefully evaluate this, and you are going to discover that the energy release will be 4.59 times 10 raised to power minus 12 joule. This is the energy release when the alpha particle nucleus are fully separated into its basic particles, protons and neutrons. We are going to move to the next slide to continue with our study. So now we have the next question, and it says calculate the amount of energy released by splitting 10 grams of uranium-235. Just splitting 10 grams of uranium-235. Remember, a mole of uranium-235 contains how many grams? 235 grams. But we are not just going to convert all these mole into energy. Just we want to find the energy that will be produced when only 10 grams of this is converted to energy. And then we have the mass of uranium given, and the mass of neutron given in atomic unit, and the mass of proton given in atomic unit. One atomic unit in terms of energy is 931 mega electron volt. And remember, don't forget, 1 electron volt is equivalent to 1.6 times 10 raised to power minus 19 joules. So now we are going to start our calculation. Remember the step again, find the mass defect. So now we have the mass defect given by this formula also on the screen. So now we are going to substitute. How many protons do we have in uranium-235? Of course, 92. We have 92 protons. And then, since the total number of particles is 235, it means that the number of neutrons will be 235 minus 92, or that will give us 143. Then, having obtained all this information, then we calculate mass defect. 92 times the mass of the proton given, which is already given here, 1.0087. That's for neutron, and then 1.0073 for proton. So now we're going to put that of proton multiplied by 92, and that of neutron 1.0087 multiplied by 143, because there are 143 neutrons in the nucleus of uranium-235. And remember, the mass of the uranium nucleus is given as 235.0440 atomic mass units. So we subtract that. Then using calculator, we simplify all this, and then we are going to have the mass defect will be the mass of the protons and the neutrons all together minus the mass of the nucleus of uranium-235. And then simply subtracting this, we have that mass defect is 1.8717 atomic mass unit. That's the mass defect. And then with this mass defect now, we now continue in our calculations. We will now continue in our calculation. So now, but we know that 1 atomic mass unit will be equivalent to 931 mega electron volt. Please, this is given here. Look at it here. It's given here. And don't forget that 1 electron volt is given as 1.6 times 10 raised to power minus 19 joules in terms of energy. So therefore, we are going to make that substitution. Convert this from atomic mass unit to energy. That will give me this times 931, and that will give us a 1742.5527 mega electron volt. Now we have that. We are going to now use the equivalent already we know. 1 electron volt is equal to 1.6 times 10 raised to power minus 19 joule. So now use that to convert this to joule. So therefore, 1742.5542 mega electron volt in terms of joule will give us this multiplied by 10 raised to power 6. Remember, mega is million, 10 raised to power 6. Then multiply by 1 electron volt, which is 1.6 times 10 raised to power minus 19. Remember, that's what we are giving here to convert to joule. So now we multiply all this out using calculator, and we're going to get our energy as 2.788 times 10 raised to power minus 10 joules. That's the energy that we are going to get when we fully convert 1 mole of uranium-235 to energy. So now, because of that, we say 1 mole of uranium-235 is having a 235 grams. 235 grams. So therefore, 235 grams of uranium-235 will contain how many particles? Already you know that. That's 1 mole. That will give us a 6.02 times 10 raised to the power 23 atoms. Then, if this contains this, then 10 grams will contain 10 over 235 times the number of particles you have in a mole. Subscribe, like, share, click for alerts. So now, that will give us a 2.56 times 10 raised to the power 22 atoms in 10 grams of uranium-235. Then the energy release then will be 2.788 times 10 raised to the power minus 10. The energy we have calculated already, multiplied by the energy we are going to get for these 10 grams containing this, because one atom is giving us that. And then we have this number of atoms. Remember here, one atom gave us this. And this number of atoms will be one atom times this number. And if we multiply that, we are going to have 7.14 times 10 raised to the power 12 joules. That's a very large amount of energy released. That's a very large amount of energy released. That's what we are saying, that nuclear energy releases much energy compared to other sources of energy like biofuel energy and other things we use here on Earth. That's why we're interested in nuclear reactions, nuclear energy and nuclear fission and nuclear fusion. We're going to move to the next slide to continue with our calculation with example number 2. And then we have the example and the information all given. The fusion of deuterium and tritium to form helium nuclide is given by this equation you are seeing on the screen. Calculate the energy Q released. Calculate the energy Q released during the reaction. The mass of deuterium is given as 2.01410 U. The mass of tritium is given as 3.01605 U. And the mass of one neutron is given by what you are seeing on the screen now. While the mass of the entire helium nuclide is given as 4.0026 U. 1 U is equivalent to 931 mega electron volt. Remember, mega is million. And 1 electron volt is equal to 1.6 times 10 raised to the power minus 19 joules. Now let's do the calculation together now. So now we have that. That's the formula, the mass defect formula. I've said this over and over. So now let's now solve that. The mass defect will give us the mass of the tritium plus the mass of the deuterium. So now that will give us this for the tritium and this for the deuterium, and then this for the alpha particle and this for the neutron that is produced. All these are here. The left hand side minus the right hand side will give us the mass defect. So now we are going to simplify that. The left hand side is, when simplified, is 5.03015. That means the mass of these two calculated together is this, while the mass of these two on the right hand side calculated now is this. So now the difference between the two will give us the mass defect. That means the mass defect as a result of this nuclear reaction will be 0.0188 U. Now that's the mass defect. The next leg is to find the energy equivalent of this mass defect. So now let's do that now. Remember, one atomic mass unit is already given in the question as 931 mega electron volt. And remember, mega means million. So we're going to use that knowledge to calculate Q. So Q will give us the mass defect times 931 mega electron volt. And when you simplify that, it will give us 17.6 mega electron volts. 17.6 mega electron volt. And we're going to convert that to joule. Remember that 1 electron volt is equivalent to 1.6 times 10 raised to the power minus 19 joules. Now, if you multiply the two, we are going to have the energy released as 2.816 times 10 raised to the power minus 12. Now we have successfully calculated the energy release. Q is equal to 2.816 times 10 raised to the power minus 12 joules. That's the energy release when this nuclear reaction takes place. That brings us to the end of this presentation. Please remember to subscribe, like the video, share the link of this video with others, click for alert so that when the next video is released, you will be properly notified. Thank you for watching.